the Green's theorem in the plane for this line integral, where C is the boundary of the region bounded by these two parabolas. And because these two functions are continuously differentiable functions, so we can apply the Green's theorem on this line integral, right? Okay, and then we verify that. Let R be the region enclosed by the given curves. The curves are y equal to x squared, this parabola, that is, this is y equal to x squared, and y equal to square root x. If we square both the sides, we get y square equal to x. So the parabola y square equal to x, that is this one. This is your origin. What is the point of intersection? From these two curves, if I put the value of y over here, so I get x square equal to square root x. Again, squaring both the sides, we get x to the power 4 equal to x, or x to the power 4 minus x equal to 0, or x into x cube minus 1 equal to 0. That means we get x equal to 0 and here x equal to 1. These two values satisfy this equation. So for x equal to 0, we get y equal to 0 from here. So we get 1 point to be the origin. And for x equal to 1, we get from here y equal to 1 square, that is equal to 1. So the point of intersection is 1, 1. You can also put the value of x over here. So this is how we get the point of intersection. Let me name this curve as C1 and this curve to be as C2. Since 3x square minus 8y square and 4y minus 6xy, these two are continuously differentiable functions in the region R. And because these two are continuously differentiable functions, now we can apply the Green's theorem on the given integral. When applying the Green's theorem, we get the double integral over the region R, curl q by curl x minus curl p by curl y dx dy. So this is further equal to the double integral over the region R. Okay. Let's derivate partially q with respect to x. What is q? It is 4y minus 6xy minus partial derivative of p 3x square minus 8y square with respect to y dx dy. So this is equal to the double integral over the region R. Let's partially derivate this with respect to x. So we get this to be as minus 6y minus partially derivating this with respect to y, we get minus 16y dx dy. Managing these two signs, we get plus sign. So this is minus 6y plus 16y. And 16y minus 6 is, so this is 10y. Please mark this as 1. So this is double integral over R 10y dx dy. Let's find out the limits for x and y. Now for this region R, x varies from 0 to 1. Yes, it is varying from 0 to 1. So x is varying from 0 to 1. And y varying from this curve to this curve. What is the value of y at this point? It is y equal to x squared. So at here we are having the value of y to be x squared. So y varies from x squared to, what is the value of y at this point? This is the curve y equal to square root x. So at this point we are having the value of y to be square root x for the values of x. So this is square root x. So x varies from 0 to 1 and y varies from x squared to square root x for the region R. So this is equal to the double integral 10y. Now because the limits of x are constant, right? So we need to interchange this. So writing here first dy and then dx. Please remember, we need to take always the constant limits on the outer integral. So the limits of x is from 0 to 1, limits of y from x square to square root x. Taking 10 outside of these integrals and integrating y with respect to y. So this is y square divided by 2 with limits x square at square root x dx from 0 to 1. So cancelling this, we get 5 over here. And now putting the upper limit for y, it is square root x square, that is x, minus putting the lower limit for y, it is, that is x to the power 4. And now integrating this with respect to x, we get integration of x is x square divided by 2 minus integration of x to the power 4 is x to the power 5 divided by 5 with limits from 0 to 1. Putting the upper limit for x, we get 1 divided by 2 minus 1 divided by 5 minus putting the lower limit for x, we get 0. So this is 5 into taking the LCM. So this is 5 minus 2. So this is 3 divided by 2. So we have got the value for the double integral on the right hand side to be equal to 3 divided by 2. And now we need to check what is the value for the left hand side. If the two values are equal, then Green's theorem is verified. Let's evaluate this left hand side integral now. The integration over C1 plus the integration over C2. Right? Let me first evaluate this integral and then I evaluate this integral and then we add these two. The curve C1 is y equal to x square. So this is equal to the integration 3x square minus 8 into y square becomes x to the power 4 dx plus 4x square minus 6x into x square, that becomes x cube. dy becomes, from here, dy is 2x dx. So this is 2x dx. Now what are the limits for x? Because this is a curve from this point origin to the point A. From here to here. That is from 0 to 1. So the limits from 0 to 1. Integrating with respect to x, we get 3x cubed divided by 3 minus 8x to the power 5 divided by 5. Limits from 0 to 1. Plus, multiplying this 2x inside, we get 8x cubed minus 12x to the power 4 dx. Right? Let's cancel these two. Putting the upper limit for x, we get 1 minus 8 divided by 5. And when putting the lower limit, we get 0. Plus, integrating this with respect to x, we get 8x to the power 4 divided by 4 minus 12x to the power 5 divided by 5. Limits from 0 to 1. Cancelling this with 2. Putting the upper limit for x, we get, if I solve this first, I get 2 minus 12 divided by 5. And when putting the lower limit, we get 0. So this becomes 2 minus 12 divided by 5. Right? 1 plus 2 becomes 3. And minus 8 by 5 minus 12 by 5 becomes minus 20 divided by 5. That is 4. So this is minus 1. So this value is negative 1. Let's evaluate this integral now. So this is equal to the integration, okay. C2 curve is from the point A to the origin. That is, the limits is from 1 to 0. Okay, now replacing y with square root x. So this is 8 into x dx plus here 4 square root x minus 6 into x into square root x. dy becomes 1 divided by 2 root x dx. So writing here 1 by 2 and here I am writing 1 by root x dx. So this is equal to integration from 1 to 0, 3x square minus 8x Plus, if I take dx outside of this integrand, multiplying the square root x inside, we get 4 minus 6x, right? If I also multiply this 1 by 2 inside, I get 2 minus 3x. And minus 8x minus 3x becomes minus 11x. Minus 11x. So integrating this with respect to x, we get 3x cubed divided by 3 minus 11x squared divided by 2 plus 2x and the limits from 1 to 0. Let me cancel this 3. When putting the upper limit, we get 0 minus when putting the lower limit, we get minus 5 by 2. So that is equal to plus 5 by 2. So we have evaluated this to be 5 divided by 2. So let's add these two now. Minus 1 plus 5 divided by 2. 3 divided by 2, which is same as that of the right hand side of this equation 1. So let's write this. From 1 we get the given line integral. The value of this line integral is 3 divided by 2. That is also equal to the value on the right hand side. That is the double integral of curl 4y minus 6xy with respect to x minus curl 3x square minus 8y square with respect to y dx dy. So both these values are equal to 3 by 2. Hence the Green's theorem is verified. The Green's theorem is verified. Okay, thank you.